Thank you very much for the invitation. Several years ago, I graduated from compactified theories to theories in infinite spaces, R2, R3, R4, whatever it is. And I will tell some results related to that. In particular, I will tell you about theories with ZM1 form symmetry and rows of center vortices and monopoles. This is the work I did with Tin Süleyman Pasic and Mendel Guen, my student. And let me start. So in the 70s, there were two pictures of confinement. One of them is, due to magnetic monopoles, people thought that it is some sort of dual superconductor. These are the people who advocated that. And condensation of these magnetic monopoles lead to dual Meissner effects. And however, these are words, and concrete mathematical and physical realizations of this idea, there was one already in the 70s, the work of Polyakov, Young-Mills plus a joint Higgs system, where monopoles are instantons. It's an analytic demonstration of mass gap and confinement. And on R4, it came quite late. In the work of Seiberg and Witten, where you have a supersymmetric theory and you break it softly to n equal 1 super Young-Mills. I'm sorry. I think I should stay here because of the microphone. So, and on R3 cross S1, around 2007, me and my collaborators understood these special theories, QCD adjoint on R3 cross S1, and we were able to solve it analytically. And in this case, both the monopoles as well as the magnetic baryons play prominent roles. But there was another scenario, which is, again, one of the people who came up with the idea is 't Hooft. And the idea is that in gauge theory, there are these codimensional two objects, and these are called center vortices. These are like points in two-dimension, lines in three-dimension Euclidean setup, and surfaces in four-dimension. And their proliferation supposedly signals the onset of confinement. There is a large lattice community who quite favors this scenario, but there is no analytical treatment of this setup in dimension greater than 3. And even in dimension d equal 2, the first semi-classical realization of this center vortex related confinement is shown fairly recently in my work with Yuya Tanizaki. Now, lattice experiments versus theory. So our current understanding of these center vortices is primarily based on numerical experiments and heuristic arguments. And I put a number of people here. You may or may not know them. The blue ones are the ones I talk from time to time. Okay, and this red one, you use the slide due to him in almost many of the talks. So in case you don't know the name, I'll put the picture so that you will recognize. Okay, so these folks will tell you something, and the thing that they will tell you is that if you keep these vortices, these vortex-only configurations account for confinement, deconfinement, chiral symmetry breaking, and stuff like that. And if you remove these configurations, whatever that means, and they will not, none of these properties are present. They will also tell you that vortices do not lend themselves to an analytical treatment. On the other hand, on the confinement mechanism I mentioned in 2-page earlier here in these theories, there is not even a mention of center vortices. Okay?
So in 3 dimensions, a vortex is a dual to a photon.
Yeah.
So button 4.
No, electric. It's a vortex electric charge. Yeah, okay. But you know, to my mind, this is one of the serious theory versus numerical experiment conflicts ever. You know, it is a disagreement of concepts, not pure numbers. And today, a wise man sitting in the front row said that you cannot debate with a computer, but you can debate with.
I said argue.
Okay. There are multiple attitudes here. One of them is to be dismissive about this numerical data. And retrospectively, if you are a lattice theorist, you can be dismissive about this continuum monopole, induced confinement, blah, blah, and not talk to each other and not care. The other attitude is try to understand interesting gauge theories in these dimensions 2, 3, 4, and from an inclusive perspective, you know, philosophically similar to Polyakov's idea. If you read his book, devotedly, you live with this impression all the time. By this, what I mean is that try to understand Johann Litt's gauge theory on the same footing with the Seiberg-Witten theory. So it is very clear that we need some new analytical methods that allow us to determine the roles of center vortices and their relation to monopoles in a framework in which the two coexist. And such a framework is built only recently, and it's something I think quite interesting. The idea is to build an effective field theory based on ZM1 form symmetry and use an idea called deformation class. It is also stated by Nati Seiberg some years ago, but there were no practical implementations of it. Okay? This is an interesting idea. The idea is that we start with a gauge theory, and for simplicity, I will assume that the only symmetries of the underlying theory, the only global symmetries of the underlying theory is ZM1 form symmetry and time reversal, and there is no mixed or pure anomalies. And I will also assume there is either exact or emergent Poincare symmetry in the infrared. So whatever I talk about applies to both lattice gauge theory as well as continuum theory. You can assume you can relax these assumptions and build other things. Let me tell you the idea. So let me first tell you what is ZM1 form symmetry is. This is the notion of confinement, the cleanest notion of confinement, relies on the ZM1 form symmetry. So you can then Wilson loops become order parameter for the symmetry, and you can make a precise statement about the nature of confinements. The question is following. Let us take a gauge theory whose only microscopic symmetry is ZM1 form and time reversal. I put this for simplicity. And this class of theories, includes pure Yang-Mills, ZN gauge theory, or pure Yang-Mills with adjoint matter, as you wish. So strategy is following. We start with a phase with broken ZN1 form symmetry. For example, you can say, oh, this phase does not exist in pure Yang-Mills. But it does. If you have two adjoint fermions to pure Yang-Mills and give a wave to both clock and shift, you break it to Zn. This is the deformation. This is still in the deformation class of the pure Yang-Mills. It's already there. Okay? So this phase is a Higgs phase, totally Higgs phase, and it's sometimes also called topological BF phase. I will use BF almost constantly. So the Lagrangian of BF theory include these two fields, this A field, which is a one form, and B field, which is a D minus 2 form. And there are, in the game now, there are two ZN symmetries associated with these two. And the basic correlation function in the game is the relation between these two, which gives you their mutual statistics. If the C links with that V, it will give you a pure phase. Okay? So, however, I tell you now, there is this symmetry here, but in my underlying theory, we will play a game from now on for a while. I will say, hey, here is a symmetry. This is actually an emergent symmetry of the BF theory. And I will say, this is not assumed microscopically, so let me break it. So I will introduce objects with gauge charge coupled to this B field. And guess what? These are center vortices. These are codimension 2 objects. But when you do that, something strange happens. You immediately gain a U1 magnetic symmetry. Okay? In the epsilon, if I did not break this, if I did not introduce this field coupling to B field, these the monopoles wouldn't be gauge invariant. But now, in this coupled theory, monopoles become gauge invariant, and I do gain this U1 shift symmetry. In Polyakov model, for example, this is the magnetic field, which is a current, and gradient of it now is 0. And you don't want U1 shift symmetry. You say, I don't want this symmetry either, and you write some operators, and you try to get rid of it. I must say that here you can dress, maybe I will say it a bit later. Okay. You can dress the monopole operator with these vortex fields, and that will be gauge invariant. And that's now we have multiple possibilities. One of them to have neither vortices nor monopoles proliferating. We will have both vortices and monopole proliferating. We will also have vortices proliferating, but monopoles do not. There is no phase in which monopole proliferate and vortices do not, because if vortices are heavy, so are the monopoles. Now, I will play this game in 2, 3, and 4 dimension again and again, okay? In 2 dimension, we have 2 symmetries. One of them is one-form symmetry, the other is a zero-form symmetry. And the vortices are instantons, similar from abelian X model, and monopoles do not exist. So we can break this ZN0 symmetry by adding these operators to the Lagrangian, and immediately you obtain this deformed BF theory. Now, this assumption that, unbroken ZN one-form symmetry is not robust because, this term immediately induces confinement. I will show it more explicitly now. You can go from this language of abstract Lagrangian to the language of statistical field theory. I always statistical field theory quite a bit. And here is the thing. This is my Lagrangian. I expand my partition function into the fugacity similar to cluster expansion. And I can write partition function like this. And these are my vortices. I can do this. It is easy. Here I need to do some Poisson resummation. And here is the result. And these are the energies. You could have obtained the same result very easily if you were to use the equations of motions for A fields. It would give you this result trivially. It's an example of localization. What happens when you insert a Wilson loop? Things get more interesting. So first of all, this Wilson loop has a non-trivial mutual statistics with these vortices. So if these vortices is inside the Wilson loop, they acquire these extra phase. Hence, you can show that for the large Wilson loop, you will get a finite string tension, okay, which depends on the anality, on the symmetry of the theory. This is very nice. You show that these extra phases plus proliferation of these center vortices gave you the area law. This is a very common assumption, also in 3 and 4 dimensions. But we will see that this assumption, this perspective is not true in 3 and 4 dimensions. So I just put here this question, whether this thing is true or not in 3 and 4 dimensions. Okay? Now let us graduate to our 3-dimension BF theory. We have 2 one-form symmetries, and now vortices, as Misha pointed out, are particles, and monopoles are instantons. And we break this ZM one-form symmetry by introducing a scalar, which this is the vortex, coupled to, with a unit gauge charge coupled to B, okay? I can write this down, but I can also write a kinetic term. It is slightly irrelevant, but it is dangerously irrelevant maybe, so it doesn't really matter. But now, as I said, when we do this, the monopole operator, which wasn't gauge invariant in the original BF theory, becomes gauge invariant here, because we can dress it with this phi quanta. This is the dressed monopole operator. But I do not want this U1 shift symmetry. So what do? I add a monopole operator to my Lagrangian. Okay? I also add kinetic term for the Maxwell field, because I know that it will be generated. It is naively irrelevant, but strictly speaking, it is dangerously irrelevant, and you will see why. This is my deformation class, and it includes everything, essentially. Now let us see what happens. This is my Lagrangian. If this vortex field is heavy, I can set this 0, set that to 0. And kinetic term of B and kinetic term of A are irrelevant compared to the topological term. So I reduce to the BF theory, Higgs phase. If that scalar condenses, then B gauge field acquires a mass. So I can drop the topological term now. I can drop anything related to B. So the Lagrangian becomes this, which is quite familiar. This is Polyakov's compact QED. It confines. Now, if phi condenses, and if we also assume this U1 shift symmetry microscopically, which forbids the monopoles, but not vortices, this is very important, the long distance theory becomes pure Maxwell theory. And the phase diagram is actually this. You can go from this BF phase to a Coulomb phase if there are no monopoles in the game. And you can get rid of the monopoles by using proper method, Lagrange multipliers. Or if the monopoles are the game, you can go from BF phase to confined phase. There was this nice Piles type instability argument which appeared in Mike Tepper's talk, and I want to tell you what happens to it. Because this argument, often taken by the lattice gauge theorists, is the evidence for confinement by center vortices. So the action of minimal vortex loop is something like this. You can calculate it. But if you have a loop of length L, the number of non-backtracking loops is exponential of log 5 divided times L. Now you see that that's a competition between Boltzmann suppression and entropy. And you see that there is a beta critical, and if you are beta larger than beta critical, vortices cannot proliferate. They remain tiny, small things. If beta less than beta critical, vortices proliferate. So this commutation relation, this relation And the fact that, the vortices, proliferation of vortices in the lattice literature is often perceived as confinement, something leading to confinement. But actually, I will prove you rigorously that this is a signal of a phase transition from a BF phase to a Coulomb phase. These phases, which look very nice, has nothing to do with the confinement. It not has nothing to do, is not sufficient to produce confinement. They are important to go from Higgs phase to a Coulomb phase. Now, I will prove the statement I made in 4 dimensions. Okay? But first, let me tell you what happens in 4 dimensions. This is probably the most interesting case. Symmetry is, there is a one-form symmetry, and there is also a two-form symmetry. Now, vortices are strings, and their word volumes are surfaces, closed surfaces, and monopoles are particles. We can break this two-form symmetry by introducing vortices with gauge charge 1 coupled to this B field. And again, we gain an unwanted U1. This is, similar to 3-dimension. And we can get rid of this by introducing monopoles because, monopole currents violate this already. Now, I'll show that if vortices are heavy, we will be in the Higgs phase. If vortices proliferate and monopoles proliferate, we will be in confined phase. If vortices proliferate and monopoles are heavy, we will land on Coulomb phase. Now, to isolate the effect of vortices from monopoles, we can use a formulation called modified Whelan due to Süleyman Pasic and Gatringer. Okay, yeah, I put reference there. Okay, here, this is the Zien field, and I introduce a Lagrange multiplier, which is a continuous field. Okay, now this tells me that I gain this symmetry. The question is, what happens? And there are no monopoles now because I put a Lagrange multiplier to get rid of the monopoles. Okay. So what happens in the beta goes to 0 limit, which is very strong coupling in the original formulation? Actually, you can do some very nice manipulation here. You can construct exact lattice duality, which swaps gauge coupling with its inverse, beta goes to 1 over beta. And it takes this Lagrangian to that Lagrangian. In this Lagrangian, the dynamical field is discrete and Lagrange multiplier is continuous. But their roles do get swapped. Here, dynamical field is continuous because it is that, and the Lagrange multiplier is discrete. It tells you that the dual of Zien lattice gauge theory with modified Whelan action is a U1 gauge theory with magnetic matter with charge N. In dual formulation, look at the position of beta. Beta appears like gauge coupling. It is not 1 over gauge coupling. That was, okay, its role is like gauge coupling. And we are considering the limit beta goes to 0, which corresponds to very strong coupling in the original model. And there are charge M monopoles, but because of the weak coupling, they are super heavy. So Coulomb phase is manifest. Now you can reintroduce monopoles, but make them heavy. Okay. Now I am considering U1 gauge theory. This explicitly breaks this shift symmetry. In dual description, now we have a U1 gauge theory coupled to charge N monopoles and heavy charge 1 electric matter. Don't let the language confuse you. Remember that in Seiberg-Witten theory, we describe monopole point and ion point by SQEDs, but the dynamical fields in SQEDs are magnetically charged. Okay, so and because the electrically charged stuff are heavy, they do not impact the low energy dynamics, and Coulomb phase persists. So the phase diagram is this. For This part was known from lattice simulation, and I forgot to put references there. But you have this BF phase, you go to Coulomb phase from there, and you go to confined phase on this line, okay? But our claim is that even for n equal 2, if you crank up these masses for the monopoles, okay, the term for the monopoles, you will go to a Coulomb phase, and our friends are checking this with simulations. I am almost done with that part, but I told you something. Okay, very nice. I told you that in 3 dimension, it is proliferation of the monopoles that causes confinement, and in 2 dimension, it is necessarily proliferation of the center vortices that cause the confinement. And in fact, we can realize this in semi-classical scenarios. On R3 cross S1, in QCD adjoint with heavy fermions, we have center stability, and you can show that there's a monopole-induced confinement. On R2 times T2 with 1 unit of 2 Hooft flux, you can actually show that center vortices lead to confinement. Here is a striking thing. The expansion parameter in both cases is the fractional instanton action and at weak coupling. They both explain non-perturbative phenomena like string tension, fractional theta dependence. And guess what? Both are continuously connected to R4. There are no gauge invariant order parameters, which can distinguish small S1 or small T2 from large S1 and large T2. But these are 2 genuinely different mechanisms but they must be adiabatically connected, okay? These are genuinely different confinement mechanisms because if you look to a Wilson loop and look what is the effect of a monopole, in the monopole background, Wilson loop essentially calculates the solid angle subtended by the monopole point. It is this. But if you take center vortex, if the vortex is inside, you get this phase. If it's outside, you do get this. It looks like they are totally unrelated, honestly. But now let us do the following. Let us compactify R3 times S1 to R2 times T2. And these are 2 related works by me, Thomas Schaefer, and my student Güvendik, and also Yui Hayashi and Tanizaki. It's a beautiful paper. And we go from, let's say, R3 cross S1 to R2 times T2. Okay? I will describe you what happens. Interestingly, this maps to this problem with twisted boundary condition on this T2, maps to a very nice problem in electrostatics. The problem is following. Let's say you have a charge between 2 conducting plates. What is the electric field of this charge at large distances? How does it decay? If it was 1 conducting plate, you would turn monopole field to a dipole field. 1 over r would become 1 over r squared. But now, this is interesting because you can use method of images, and you have to do an array like that. And guess what happens? It decays exponentially. There are multiple ways to see this, and it is not a very easy problem. It is a full section in Schwinger's old classical electrodynamics book, and it is known in the circle that know it. And the modes decay in the radial direction exponentially. So the photon is gapped out. What does this mean dynamically? It means the following. You have a monopole here. Maybe the following is better picture. You have a monopole here. Its field starts out radially, but then ultimately its field collimates into flux tube. Let me go back to this picture. What happens is that half of the flux of the monopole goes through north pole, half of the flux goes through south pole. But if you are a 2-dimensional observer, you will see this object as center vortex. it is quite striking to me that, this thing, this monopole, the effect of the monopole transmutes to this center vortex. Okay? Now, I think the set of ideas that I talked about here resolves a number of difficulties between calculable continuum theories and lattice experiments. So an implication of the analysis is that what does center vortex removal procedure means? I would say it is throwing out baby with the bathwater, okay? And some lattice people, for example, Massimo Delia told me that he actually realized this at some point. In D equal 2 dimension, proliferation of the vortices is necessary and sufficient to have confinement. In D equal 3 and 4 dimensions, these phases, the phase in which center vortex proliferate but monopoles do not, is a Coulomb phase. It is not a confining phase. In particular, the proliferation of these center vortices is necessary but not sufficient to generate confinement. If monopoles also proliferate on top of, or condense, or on top of vortices, that leads to confinement. Interestingly, in the Coulomb phase, I didn't talk about this, but it's worthwhile mentioning, you do not only get one photon. You can show that this is a detail that's present in our paper. You can start with the Z gauge theory, and you can land on a phase with n-1 photons. You may think this is very curious, but if you think about Yang-Mills theory with two adjoint Higgs fields, clock and shift, you break it down to Zn. If you turn off on R4, if you turn off one of the adjoint Higgs field, it reduces SUN down to U1 to n-1, and there are n-1 photons. Okay? So if you turn off, and monopoles are super heavy and they do not lead to confinement. And if you turn off that scalar as well, then you will go to SUN theory and presumably have confinement. But the surprising thing to me is that from a Zn lattice gauge theory, you can actually establish a phase which has n-1 photons. And the final thing is that this metamorphosis of monopole instantons to center vortex in passage from 3D to 2D. And both of them are fractional instantons. And that makes one question, what instanton means on R4? Maybe we are too naive about BPST instantons. Okay? So maybe we have to think about BPST instantons much, much, much more carefully, because whatever it is, its fractionalization in two completely different ways lead to confinement on these two different setups. Let me stop here. Thank you very much.
Thanks for a very interesting talk.
I have a question. So I would like, if possible, of course, because everything you said abstractly looks great. But let's say I have my preference. I like very much the Zyberg-Witten solution, where everything is crystal clear.
Sure.
We see there whatever, I mean, it's low energy solution, but it doesn't make it any worse in terms of its transparency.
Yeah.
We introduce the dual monopole, the dual photon, then we see that the monopoles condensed at a certain points, and then you introduce a little bit of breaking on n equal 2 down to n equal 1, period. You get the string. Okay?
Yes.
And you can explore it to any detail. It's just a string.
Okay.
Abrikosov, Nielsen, Olesen
Yeah,
string.
yeah.
Nothing more than that, nothing less. So what I have to do with this theory, in order all of a sudden, instead of a string, get a vortex picture. Because here,
there was a remark, okay, I can answer that. There was a remark that Mike Tepper made. where are the center vortices in U1 Polyakov model? Okay. The point is they are already condensed. If you do not have monopoles, Polyakov model is in the Coulomb phase. Actually, you can consider Polyakov model not with one adjoint X field, but two adjoint X fields. And you can break it to the end. The phase that we talk about, the Coulomb phase, it is already the phase that these center vortices, what people call center vortices, is condensed. So then on top of that, that prepares the medium for the monopoles for them to be able to proliferate. Because otherwise, they are connected by these junctions of n of them in the BF phase to each other, and they cannot proliferate. So, but similarly, in some sense, in continuum Seiberg-Witten theory, when you start with perturbative analysis, that's already the setup in which the center vortex is condensed. On top of that, if you have monopoles, and if these monopoles proliferate in an appropriate way, they generate confinement.
What does it mean if? Because I start with
yeah,
this
yeah.
model. Wait a minute.
Yeah.
N equal 2 super young means. Forget about your notation. I just introduce gauge fields, supersymmetrize, 8 supercharges.
Sure.
Then there is no if in this thing.
Yeah, of
and
course.
also, at first, it's n equal 2.
Sure.
I find 2 points where the monopole and the dual description are massless. Then I add by hand a little bit of n equal 2 braiding term with small coefficient. So everything is still under control.
Sure.
There is no if, there is no
Sure.
either.
What is the question?
Or you get, my question is where the center vertices here?
I have a proposal.
Why do
I
we
have
see-
Center
a radical
vortices-
proposal.
Yeah.
Let's do it over drinks.
Yeah.
No, but I think it's interesting.
Maybe
to
we should ask if
everybody.
there is another question
Yeah,
because nobody.
other,
I have a suggestion for
There
this. Imagine that there is another mechanism that he suggested has no continuum limit. No continuum limit. And
There is a
then
question,
it will
I
be
think so.
discontinuity.
yeah.
David?
I just wondered, how did the lattice gauge people remove?
Oh,
Those configurations.
that's a brutal procedure. I think in that procedure there is it is really brutal procedure. But the people I mentioned, some of them I chat with them, quite brilliant people. But some of them realizes it was also clear in some of the slides that Mike Tepper showed. There are necessarily vortices living on these. There are necessarily monopoles living on these vortices. When you say, "Hey, I am removing the vortices," they are also removing these monopoles. Because of that, in some sense, their demonstration shows the necessity of the vortices, but not sufficiency. So they do not take that step. I think the correct set of ideas, goes along the lines that I described.
But you didn't answer my question.
But
not any step. I ask you a very particular question.
that is
Where
okay.
in the
Okay.
Seiberg-Witten
I can answer. So instead of Seiberg-Witten, take an equal for super young males, do a beta deformation.
No, I don't want
No,
to
no,
do-
no.
No, I refuse to do any deformation.
No, it's
I'm an animal.
no. The idea of deformation class allows you to do such manipulations. I can add one more adjoint scalar to the game, okay? And Higgs Seiberg-Witten theory, not to maximal abelian group, but to Zn.
But it will
As
be not
I-
Seiberg-Witten
As
theory.
it will become Seiberg-Witten because as I remove that scalar from the game, then it is Seiberg-Witten, and there is a phase of proliferation. There is a Coulomb phase. That phase is a realization of the center vortex condensation.
Maybe there is, but you don't tell me in terms of cyber quantum theory at the gauge fields which we have, supersymmetrization, no B
I
fields or
think I
beta
use
fields.
my
Forget about
executive privilege to.
Yeah.